Dr. R. Sugaraj Samuel. He is working as a professor in physics at New College, Chennai. He is also training students for IIT JEE, AIEEE and BIT SAT. He has more than 16 years experience in both teaching and research. He has published a book titled The Complete Handbook of Bachelor of Electronic Science Practicals, which is prescribed for the syllabus for BSc Electronic Science by University of Madras. He has presented papers in several national and international conferences and has also conducted many training programs and workshops to motivate energetic students. His research areas are ultrasonic, polymers, crystal growth, and photovoltaic systems. He is experienced in both regular classroom teaching and online teaching as well.
Welcome to UGC lecture series in BSc Honours in Physics. We have been discussing about the subject electricity and magnetism in this part of the lecture series. We are discussing about the concepts related to magnetism in this part of the lecture series. Before we start today's lecture, let us see the session outline for today's lecture. In this session, we are going to see the magnetic hysteresis in detail, some of the terms like retentivity, coercivity and magnetic energy from the hysteresis curve, and finally uses of magnetic hysteresis curve. What is magnetic hysteresis? What category of the magnetic material exhibits this property? Actually, the strong magnetism is found in ferromagnetism among the three types of magnetic materials. What are the three types of magnetic materials? Diamagnetism, paramagnetism and ferromagnetism. In the case of ferromagnetic materials, due to spin exchange interaction, which is one alignment interacting with the other alignment to form domains, and finally when external magnetic field is applied, these domain fields which already have a strong magnetization alignment happened in the particular region called domain, they will align in the external magnetic field. When the external magnetic field is removed, this alignment will continue, it will appear rigid because of the spin exchange interaction and all that. Only the temperature can affect this magnetization, thermal vibration can affect it. Otherwise, this magnetism is retained by it, it is very strong. The susceptibility and relative permeability are very high values as far as the ferromagnetic materials are concerned. When such a ferromagnetic material which is not magnetized originally, that means a virgin material, when it is subjected to external magnetic field, how does it behave? That behavior of this material is called magnetic hysteresis. Actually, the word hysteresis means lagging behind. Shall we see the typical definitions on the slide? When an iron bar is magnetized slowly by a magnetizing field H, whose strength can be changed, it is found that the magnetic induction B inside the material increases with H and then attains a saturation. This is depicted by the path OA in the figure. Here I have shown the magnetization cycle diagram. When the material is not magnetized originally, it is starting from the 0 0 because there is no magnetic induction found in the material and magnetizing field is also 0. We should have the facility to vary the magnetizing field. So, in such a condition we are doing it. This kind of experimental observations can be done with a ring called Rowland's ring, which is nothing but a toroidal coil which would produce a strong magnetic field at the center, and the specimen under study, this ferromagnetic material that we have taken up, should be kept in the toroidal coil, center of the toroidal coil, and the current has to be varied. As the current is changed, increased from 0 to a higher value, the magnetic field also is likely to increase, magnetizing field, and there must be a facility to reverse the direction of current in the toroidal coil. So, thus this experiment could be completely performed throughout the cycle. Follow this instruction. It starts from 0 0, and as the magnetizing field increases, the magnetic induction is also increasing with this trend and reaches a saturation. Beyond that, we cannot change the value. What is the meaning of attaining a saturation? That means it is not further going to change. Why? Because this magnetizing field has made all the dipole moments existing in the domains to align in the external direction. So, no further alignment is possible. That means it has attained saturation. So, that is what is shown here as the section of the graph OA. Beyond that, if you increase H, what will happen? The B would have reached a saturation value. Beyond that, the B will not increase. That is the meaning of saturation. Now, what further we can perform? We can do, because anyway increasing the current or increasing the magnetizing field H is not having any meaning. B has attained a saturation. Now, we will reduce the current or reduce the H value, decrease the value. Now, a strange effect is found. Shall we see what it is? If the magnetizing field is decreased slowly, then magnetic induction also decreases, but it does not follow the path AO. Instead, when H becomes 0, B has a non-zero value equal to OB marked in this diagram. I would like to retrace the path and explain from the diagram. From the starting point, when it was magnetized first time, it has taken the path OA, reached a saturation, and then when the H is reduced, it is not taking the OA path again, it is coming in some other path. It reaches the point B. The B point, what is the importance of it? When H is brought to 0, still there is magnetic property. The magnetic induction is still found in the material, which is marked here as B. So, this is a magnetic property that is existing in the material. What is that called? This implies that some magnetism is left in the specimen called remanence or residual magnetism. This part, I would like to show that part. This is existing. Even when the H is brought to 0, this much of magnetic induction is found in it. What does that mean? It has retained the magnetism in it, right? That magnetism is going to be the permanent magnetism retained by the ferromagnetic material in the absence of the magnetizing field. Further, when we decrease, because it has already come to 0 H, but we have the option of reversing the direction. When we do that, what will happen? Let us see the diagram for it. Further, when the magnetizing field H is reversed, the magnetic induction decreases and becomes 0 at C. Where is the point C? It is here. See, after the H is brought to 0, H is reversed, and now the magnetic induction B is becoming 0 at a particular point. But this is not happening on its own. This is with the influence of H is existing in the reverse direction. So, once a material is magnetized and when the external magnetic field is removed, it is retaining some magnetism in it. That is called the remanence, which we have seen. When the direction of H is reversed, so that the magnetic induction is brought to 0, but it is happening in the presence of again an external magnetic field H in the reverse direction. So, it is very difficult to bring the material to 0, 0 position again. And in the presence of the external field in the opposite direction, the magnetic induction B, capital B, is brought to 0, no? That is called the coercivity. So, how much of external magnetizing field in the reverse direction is required to coerce the material to have 0 magnetic induction? Coerce means what? It is influencing, making or requesting to lose the magnetism. It is losing the magnetism, but in the presence of the external magnetic field or magnetizing field. So, that is called coercivity. Thus, to reduce the residual or remnant magnetism to 0, the applied magnetizing field OC in the opposite direction is called coercivity. It is required. This OC is required. So, it is called coercivity. Further, when we increase the magnetic field, the magnetizing field H, what will happen? It will once again reach a saturation, is it not? That is what is shown here. When we further increase this H, what will happen? It goes to the saturation in the reverse direction. So, the reverse direction also would have reached a saturation. That means the alignment is happening in the reverse direction. After that also we can reduce the H value and bring it to 0. So, once again the same remanence is there, retained magnetism. Once again change the magnetizing field direction and this F is attained. Look at the way in which the directions are shown. It never brings the material to 0, 0 point again. That means ferromagnetic materials, they remember their history, how they have been magnetized. It is very difficult to bring them to 0, 0 condition again. Once magnetized, it is magnetized. Once it is disturbed magnetically, it is disturbed forever. It is possible to bring to 0 magnetic condition with the external field in the opposite direction. In the 0 magnetizing field, it already retains some of the magnetism. So, this kind of behavior is called magnetic hysteresis. This has got a lot of significance too. Let us see further what are the significance we have. The word hysteresis literally means lagging behind, which is seen that the magnetic induction B lagging behind the magnetizing field H in a cycle of magnetization. This phenomenon of lagging of magnetic induction behind the magnetizing field is called hysteresis. Hysteresis is a closed loop over a magnetization cycle. Look at this diagram. It is a closed cycle. Only the starting point is from the origin, otherwise it covers a area, it is a closed path. And when a material is subjected to magnetization cycle repeatedly, you increase the magnetizing field in one direction, drive the specimen to the saturation condition and then reverse the direction of H, study about the remanence, how much it retains, and reverse the direction of H, study about the coercivity, how much is required to bring it to 0 B condition, and then once again increase the magnetizing field H in the opposite direction, it reaches the saturation again. All these are happening because of the physical movement of the dipoles. Though we say domains are formed, in the domains the directions are changing when the magnetic field is changed. The physical movement of atoms or molecules possessing the magnetic moments happen. So, that movement will eat up the energy present in the material. Each material has got its own strength, its own energy. So, this movement, what will happen when a material is moved like this? It is aligned and then alignment is changed. This kind of vibrating motion, no, if it is happening repeatedly, the magnetizing cycle, repeated magnetizing cycles do this kind of movement in the magnetic dipoles. Dipoles are formed by atoms and molecules. Atoms and molecules, they themselves orient and move, all that. So, the energy is utilized. So, this area itself is telling about how much of energy is lost. In what form this energy is lost? It will be lost in the form of heat, because the movement, vibrations will produce heat in materials. So, it has got a significance. And the shape of the hysteresis curve, that also has a meaning. It could be thin or it could be wide. Accordingly, they have several applications in materials. What are they? We will look at these applications. The shape and size of the hysteresis loop is the characteristic of each material because of the differences in their retentivity, coercivity, permeability and susceptibility and energy losses, etc. By studying hysteresis loops of various materials, one can select a suitable material for different purposes like design of electromagnets, designing of permanent magnets, and also materials for transformers, the cores of transformers. So, for all these, the shape of the hysteresis curve is useful. In what way? Have a look at this slide. The energy spent in magnetizing a specimen is not recoverable, and there occurs a loss of energy in the form of heat. This is so because during the cycle of magnetization, the molecular magnets in the specimen are oriented and reoriented a number of times. This molecular motion results in the production of heat. It has been found that the loss of heat energy per unit volume in each cycle of magnetization is equal to the area of hysteresis loop. What is the energy that is lost in one cycle? It is equal to the area of the hysteresis loop itself. This area could be a large area or a lesser area. Thus, the energy loss could be a higher value or a lower value. Thus, they have different applications. Have a look at this diagram. There is a category called hard ferromagnetism or hard ferromagnetic materials. These materials will have a broad hysteresis curve. On the other hand, soft ferromagnetic materials, they have a thin hysteresis curve. Obviously, the area on the left hand side is larger, the area on the right hand side is smaller. It is a thin area only. What about the values of retentivity? Look at the retentivity here. This is the retentivity, right, which we have marked. This is the retentivity. So, for permanent magnets, this kind of hysteresis loop is preferred. What materials do have this kind of broad? For example, steel has that. Steel has this kind of broad area. So, they will retain the magnetism to a greater extent. Because the loss is very high, these materials should not be subjected to repeated magnetization cycle, because each cycle it is going to lose energy. So, subject it to 1 or 2 magnetization cycles, and try to keep the magnetism in them because of the high retentivity value. For soft ferromagnetism, what is there? The area is less. Of course, the coercivity is less, and simultaneously the coercivity is this. The retentivity is less. Coercivity is also less. Here the coercivity is also very high, right? That also we should understand. And these materials can be subjected to repeated magnetization cycle. The best example is soft iron. Soft iron normally has this kind of very thin hysteresis loop area. So, these materials are accordingly used. These soft iron materials could be used for the electromagnets. Electromagnets are normally subjected to repeated magnetization cycles, and the energy loss is also found to be less in these materials. So, in the case of transformer core, we will have this soft iron material, maybe a kind of alloy, which should have a very thin area, because it is going to be subjected to the repeated magnetization cycles. The alternative current will vary 50 times in a second. So, accordingly the magnetization will be varying, and the electromagnetic induction is the principle of magnetic material found in the transformer materials. So, accordingly we have to choose the materials. Ferromagnetic materials have lots of applications. We will see 1 or 2 applications of them. To form the permanent magnets, the ferromagnetic materials are used. The ideal material for making permanent magnets should possess high retentivity, that means the residual magnetism, and high coercivity, so that the magnetization lasts for a longer time. Examples of such substances are steel and alnico. It is an alloy of aluminum, nickel and cobalt. So, this is one application to form the permanent magnets. Ferromagnetic materials are used. The next application I would like to take up for discussion is electromagnets. Material used for making an electromagnet has to undergo cyclic changes. Therefore, the ideal material for making an electromagnet has to be one which has the least hysteresis loss. Moreover, the material should attain high values of magnetic induction B at low values of magnetizing field. Soft iron is preferred for making electromagnets as it has thin hysteresis loop and low retentivity. It attains high values of B at low values of magnetizing field H. One more application we will see, it is the core of the transformer. A material used for making the transformer core and choke is subjected to cyclic changes very rapidly. Also, the material must have a large value of magnetic induction B. Therefore, soft iron that has thin and tall hysteresis loop is preferred. Some alloys with low hysteresis loss are radio metals and Pern alloy and mu metal. These are some of the alloys which have very low hysteresis loss. The specially designed materials to have high magnetic induction B for a very low H, the magnetizing field. We will see one more use of the ferromagnetic material, which is found in the magnetic tapes and memory storage. Magnetization of a magnet depends on not only on the magnetizing field but also on the cycle of magnetization it has undergone. Thus, the value of magnetization of the specimen is a record of the cycles of magnetization it has undergone. Therefore, such a system can act as a device for storing memory. Ferromagnetic materials are used for coating magnetic tapes in cassette player and for building a memory store in modern computer. So, these are the applications of ferromagnetic materials, and there are a lot more applications which you could find out in some of the reading materials and from the resources available for you. Now, we have come to the end of this lecture. Before I wind up, shall we see the summary of today's lecture? In this session, we have seen the concepts of magnetic hysteresis in detail, some of the terms like retentivity, coercivity also we have learnt, and the concept related to the magnetic energy that is used in a hysteresis curve and uses of magnetic hysteresis curve pertaining to the ferromagnetic materials. Before we wind up this lecture, we will test our understanding by answering these questions. Explain the magnetic hysteresis of ferromagnetic materials. Define the terms remanance and coercivity. What is the physical meaning of the area of the hysteresis loop? Mention the uses of ferromagnetic materials. With this, I would like to conclude the lecture topic on magnetism. See you in other lectures with the concepts related to electricity and magnetism. Thank you for watching this program.